Okay, so I'm audible, right? Hello?
Yeah, ma'am.
Yeah, okay. Can you mute yourself maybe? It's too much. Yeah, okay. So this is the second class, and here we will continue and extend to what we were doing in the last time. So the outline of this classes is such that we will discuss some of the basic concepts and then we'll try to solve certain problems. So I'll discuss the solutions and we'll work out the solutions together. And then we will discuss if we have any doubts and try to clear them. So okay, so this was already done in the last class that so what is the first law? What is the expression for the first law? And what are the different response functions like the specific heat at constant pressure or at constant volume, and then the compressibility of the gas or the expansivity. So these are response functions, meaning that this is how a system responds to mm, a given external condition. So if you apply heat, how much temperature rise and all of that. So these are response functions. And we know that the second law gave us the concept of entropy. And from there, we could define the state function, which is given as S is given as dq ds, delta S is given as dq by t. So these are the basic concepts that we already know and have idea of, correct? So what we will now do is we will try to solve certain questions are uh, which use these concepts, and then finally this class we will spend most of the time talking about Maxwell's relations and how those can be used to find expressions for certain quantities and solve some problems related to that. Okay. Okay, so you can see the question, right?
Yeah, ma'am.
Yeah. So here we will try to derive the expression for the heat absorbed in these different processes. Okay. Now consider that you have a system which is an ideal gas, and then it undergoes a process which is characterized by this PV to the power n equal to constant. Now the value of n depends on what kind of process we want to deal with. So can you tell me that for an isobaric process, what will be the value of n? Any idea?
During isobaric process, pressure is constant, isn't it?
Yes, yes. Isobaric process means pressure is constant. So in this expression, PV to the power n equal to constant, what is the value of n for an isobaric process? So it's pretty simple, right? See, we want P equal to constant. So
Yeah.
what should be the value of n here so that this terms goes away?
I have no idea. I think there is lots of other disturbance sound, no?
Yes. That is there. You can even try writing in the chat box. If you want, you can write in the chat box whatever solution you're thinking to be correct. You know, there's a chat box, right? Do you know where is the chat box? You'll see this chat kind of symbol coming in. So you can even write there. So,
I am trying to rotate my camera, but I'm not able to rotate.
no, no,
I
you
think.
don't have to. You don't have to rotate your
Oh yeah.
camera. So what you have to do, yeah. So what you have to do is you can go to this okay, one second. So so maybe if I open Teams, one second. See, you'll have this chat option here, so you can maybe write something here if you want to write. Okay, you can write the solutions here. Correct? Uh, okay. So what I'll do is I'll again maybe share. Okay. Okay. So
I am able to give the answer.
hmm,
So I think I am using phone, so there is a problem
yeah,
to
it's
type.
yeah, okay. So let me tell you then. So here so we want P equal to constant for an isobaric process. That means if n is set to 0, so anything to the power 0 is 1, right? So that means then this will be P equal to constant. So for an isobaric process, we will have n equal to 0. What will
Oh yeah,
happen for a yes. Now what will happen for an isothermal process? For an
uh,
isothermal process, we yeah, tell me.
yeah. Isothermal, that means temperature is constant.
Yes, okay. And for an ideal
Uh,
gas, we know the equation of state is PV equal to nRT, correct?
yeah,
So so in isothermal, that means nRT is constant. That means PV equal to constant, correct?
yes.
Okay, so that means here n should be equal to 1 for an isothermal process. It's clear, right? Hello?
Yeah, ma'am. It's clear.
Yeah. And then if you have an isocodic process, that means it's the extreme, it's the other extreme where so isocodic means the volume is constant. So in that case, we can set n to be infinity. Okay.
Yeah.
And then for an adiabatic process, we know that the expression is PV to the power gamma equal to constant. So in that case, n is equal to gamma, which is the ratio of the specific heats. Okay. So if we use those concepts and choose the value of n accordingly, we will see how we can find the expression for heat. So we want to find the expression for heat. Okay, I don't know what happened. Go one second. Yeah. Okay, so we want to find the expression for heat. So what we will do here is, so this is how we find the values, different values of n for different processes. Now, from the first law, we know that dq equal to cv plus p dv, right? So here we all, because cv we know it is given as del u del t. So accordingly, we find dq equal to cv plus p dv. Now, how do we find the heat absorbed? This is in terms of a differential. So we have to integrate it in order to find the total heat that is absorbed in the process. So here we integrate from the initial state to the final state. So it's given as CVDT, integration of CVDT plus. Now P is replaced by some constant A by V to the power N. So this is the general expression, correct? And then we do the integration and this is what we get. Now this is for all values of N, given the condition N not equal to 1. So for any values of N where N is not equal to 1. What happens when N is equal to 1? So in that case, we cannot do it in this way. Here we have to, it will be A by V dV. So then it will come out to be in logarithm. So it's like RTI ln VF by VI. So we, these things are already done, right? So we already know how to get these expressions. Is this things clear? Okay. So, okay. So for now, for an isobaric process, what will happen here is, for an isobaric process, we know that the value of n is 0, correct? We just found that the value of n is 0. So we put the expression here and this is what we get. Now, what happens for an isothermal process? What will be the expression that we will be using?
Yeah, temperature is constant.
Yes,
So
temperature is constant. Yes. So
so the
what
change
should
in
be?
temperature will be zero.
Yes, the change in temperature will be zero. So if you look at this expression, this term is going to be zero, correct? And then we will be using this expression. Why? Because in this case, n is equal to 1. We just found out that for isothermal process, n is equal to 1. So this is the expression that we will be using. So for an isothermal process, it's given as RTI ln Vf by Vi. This is the expression for heat absorbed. Now, what happens if we have a isochoric process? That is where the volume is constant. How do we proceed with that?
That means the Bi upon Bm term is will be, goes to zero. I think.
The which term?
This term Bf upon Bi, RT ln Bf upon Bi.
No, see, RT ln Vf upon Vi will work out only when n is equal to 1. See, we are integrating this term. So we get logarithm when we have dV by V. So that holds only when n is equal to 1. That is for isothermal process. But now we have an isochoric process. That means n is equal to infinity. So try to use the general, this is the most general form, right? When n is not equal to 1. So try to use this form and tell me what should be the expression.
N goes to infinity.
Yes. So if n
Uh,
goes to infinity, what happens to this term?
this term will goes to zero.
Okay. So the expression is only this one, right? So this
Yeah.
is what is given here. So here this goes to infinity. So that means this term goes to zero. And this is the expression for the heat absorbed in an isochoric process. And then when we have an adiabatic process, we will use the general formula, which is this. And here n is given by gamma. So if we replace n by gamma and do some simplifications, we see that delta Q is equal to 0. And this is what is expected, right? For adiabatic process, delta Q is always 0. So it holds, and that means what we are doing is correct. Okay. So in this way, if you are given a polytropic process, something like this, and then if you are asked to find the expression for heat or the expression for work done, you have to work out accordingly, similar to this. So in some cases, the initial and the final values, maybe suppose if you have this expression, you have said that you are having an isothermal maybe expansion and the volume changes from Vi to 2Vi. So what should be delta Q? So it should be something like RTI ln2, correct? And Ti is the initial temperature. So similarly, you can use these relations to find the heat absorbed in different kinds of processes. Okay, this is clear, correct? Yeah,
Yeah. Please proceed.
yeah, okay. So now the second question is that, so in this case, we know that the expression for work done is PdV and we integrate and we find the work done. Very good. But then here we know that in the process, the pressure is changing from Pi to Pf and it's an isothermal process. So the pressure on a solid is isothermally increased from Pi to Pf. Now, what should be the expression of work done? And you are only given this term, which is the isothermal compressibility. So how can someone find the value of W? W is given by integration of PdV. So how do we plan to use this information to find the expression for W? Okay, so let me better, I'll try to share.
Okay. Can we multiply P in both sides?
What will happen if we multiply P in both sides?
And the right side will be only term PdV. That is work done.
So
And
you're
left hand
telling
side. Yeah, yeah, yeah.
Here,
After the injury, yeah, like the my expression is PDB is KT Kappa T B minus sorry PDB equal to minus Kappa DB.
PdV equal to minus PdV
Yeah,
equal to minus kappa.
Kappa T and P sorry D DP.
Okay, okay. So in that way, you find an expression for dV, like a relation which relates the change in volume with the change in pressure, right?
Yeah.
Yes. So let's see how that is done. You was
Yeah.
yes, something like this, right? This is what you were saying. So we multiply, it will be minus KTV into dP on one side, and we have the expression for dV. And we put it in this expression, and then we integrate. Yes. Okay. So that means, so in this way, this question tells us how this informations like this response functions can be useful in deriving expressions for measurable quantities, or so the quantities which are otherwise maybe not known to us, we can have the idea about this response functions, and from there we can find the expression for work or heat and all of that. Okay. So now talking about this thermodynamic potentials, we know about this different thermodynamic potentials and how it can be written in terms of this differentials, right? This thing is clear, correct? Huh. Okay. So now, suppose if you have this expression, can you write T or P in terms of the internal energy? So what should it be?
Yeah, man.
Yes. So the expression for T should be del U del S at constant volume. Correct. And the expression for P will be del U del V at constant entropy. So similarly, we can use this expression. So if we start with this state function, we can use this expression to find the, the expression for temperature and volume in terms of the enthalpy or the partial differentials of enthalpy. Similarly goes for the free energy, like the Helmholtz or the Gibbs free energy. But now, if you are given this, maybe if you are given this expression, can you derive the Maxwell's relations from here? Is it possible to derive?
Yeah, man.
Yeah. So so how do we do it? Like, what is the hint? If you are asked for the hint, which tells you that yes, this is possible. What is the step, the first step that you would be thinking about? Okay, so we have some, we have Anuj, I don't know, B372, okay. And then we have Jamuna, okay. So we are trying to now talk about this thermodynamic potentials and see how one can derive the Maxwell's relation starting from the thermodynamic potentials. Okay, guys, clear for everyone? Yeah, I'll consider that it's clear because I'm not getting responses. Hello. Okay, so I guess you all are alive and listening. So here, suppose if you're given this expression, you want to derive the Maxwell's relations from here. So the main concept that we will be using is that U is a state function and it's an exact differential. So that means del square U del S del V will be equal to del square U del V del S. The order of differentials doesn't matter. So let's see how we can use this expression and then derive a Maxwell relation. And similarly, you can use this concept to derive the other Maxwell's relations. Okay. So here, if you use just this expression, you know that del U del S at constant volume is T and del U del V at constant entropy is minus P. So now U being an exact differential, this is equal. which implies that now if you uh, do a differentiation of this term with respect to volume, so you get del T del V at constant entropy will be equal to del P del S at constant volume minus of del P del S at constant volume. So this, as you know, is one of the Maxwell's relations. So similarly, if you start from enthalpy and the other potentials, you can find the respective Maxwell's relations. This is clear to everyone?
Yeah, yeah.
Yeah, okay. So these are the different Maxwell's relations. And as I had shared in the last class as well, so with like using this Maxwell's relations, we can derive different quantities in terms of the other known ones. So the question that comes to us is that why do we need these relations? Are this just for solving some mathematical questions? Is that the only thing? So that's not true. So the major use of this Maxwell's relations is that so there are certain quantities which are measurable in labs, like you can measure temperature, you can measure volume, you can measure the compressibility, but you cannot measure entropy. Okay, so now if you have to find an expression for entropy given this known quantities, how do you do that? So there comes Maxwell's relations, which help us to relate the quantities which are not actually measurable in lab to the quantities which can be measured. So in this way, this Maxwell's relations can be useful. Now here, that means that, see, here we have K and alpha. These are all compressibility or expansivity, which can be measured. And then here we have the change in pressure with respect to volume at constant entropy. So if you are given these quantities, maybe you can follow this path and finally reach to this expression, which was not otherwise possible for us to evaluate. Okay. And here, while we are dealing with Maxwell's relations, we have to have this idea about the cyclic relation and the reciprocity relations. So let us just have some description about that. So here, I won't go into the details of the derivation unless you want me to. I will consider that you know this. So the two important relations that helps us to solve this kind of questions which deals with partial differentiation is these two. So if there is a function, okay, so if you have x, y, and z, these are the different variables, and then they are connected by some functional equation. Then if you find del z del x at constant y, that can be written as 1 by del x del z at constant y. And this is called the reciprocal theorem. And then we have this reciprocity theorem, which is the cyclic rule: del x del y at constant z into del y del z at constant x into del z del x at constant y is equal to -1. So these relations are very useful in solving questions, and one has to be very like very well versed in dealing with this kind of equations. Okay. So now the next question. So this question is quite similar to one of the questions.
Excuse me, ma'am.
Yes, yes.
From where we have taken this, from which book we are doing these statistical mechanics questions? Yeah, this book, yes, ma'am.
Okay, so this is a book by A.B. Gupta. You can try reading that. It's quite simple in terms of understanding. Some thermal physics book by A.B. Gupta. And the questions are from different places. So I tried to get some
Ma'am,
from
can you repeat the author name once?
A.B. Gupta.
A.B. Gupta. Thank you, ma'am.
Yeah, welcome. So the questions are from different sections. You can try solving some, maybe some are from uh, net, CSIR net or GATE questions, or some can be from different kind of textbooks, which I thought might be interesting to solve. Okay.
Okay.
So now this is the next question. So here, this question is quite similar to to one of the questions that is there in your third assignment, as I saw. So here, a given system satisfies this relation. So can you tell me that which among the following is true for this system? And the hint is to use the Maxwell's relation. So first you have to decide on which Maxwell's relation to use, depending on the options that are given here. And then can you tell me which is the answer?
It is the relation is del S upon del V equal to del P upon del T at constant V.
Correct. And so what should be the answer?
Okay.
It's pretty direct. If you know the Maxwell's relation, you can just directly sort it out. Del S del V at constant temperature is equal to, you just said, del P del T at constant volume. And so if one is zero, the other is also supposed to be
B,
correct.
the
Correct.
coefficient of condenser is, yeah.
Correct. So that means if you are given such kind of a relation, and then if you are said that what is the condition that the system satisfies, you have to use the Maxwell's relations to find the expression for for the quantity that is described in the options, and you can relate it to find the correct solution. Okay, so here the answer is B. That is 2. Okay. So now, this is another thing which I thought it's worth discussing is this significance of Maxwell's relations, which manifests itself in terms of this Clausius-Clapeyron equation. So most of you or all of you know about Clausius-Clapeyron equation, correct?
Yeah. Yeah.
Everyone? Hello? Hello?
Yeah, yes, ma'am.
Yeah, okay. Because there's no connection sometimes. So it's okay. So the Clausius-Clapeyron equation makes use of this first Maxwell's relation, and there from there what we get is this relation. Now, why this is interesting is that now if we consider a process which involves latent heat, okay, so let us consider the process where there is transfer from liquid to vapor phase, and there so there's this latent heat of evaporation that is involved here. So then we can replace the heat term as L into dm, where m is the mass differential. Okay, so there the corresponding volume change is given by the difference in, so these are the specific volumes, and you can find the expression for the volume change. So now if you replace it here, what you find is an expression which tells us that the slope of the pressure versus temperature graph at constant volume is can tell us about how the volume changes during this kind of phase transitions. So using this information, so like here they have described in terms of evaporation or vaporization, where there is transition from liquid to gas, but it can also transition can also happen from solid to liquid. So now using this concept, can you tell me which among the following is the phase diagram for water? Uh, any idea how to proceed with this?
The second curve.
The second curve. Okay, very good. So how do you tell that?
Uh, just I know, ma'am.
You know. Okay, very good. Okay, very good. But so now let's see how we get to this for
Actually,
others who don't know. Okay,
I have
so
a mind the phase diagram graph. I have in mind.
okay, so it's in your mind. Okay, so how did it get to your mind? It initially you might have studied about this, and then now you don't remember the exact relation, but you kind of remember that this is how the phase diagram looks for water, correct?
Yeah,
But
yeah, yeah.
yes, okay, but then you have to also remember the reason behind it, and that is very fundamental. It's because, see, if you look back at this expression, this tells us that depending on what this slope is, the volume will either increase or decrease. So in the first case, sorry, so in the first case, the slope is positive, and that tells us that if one moves from solid to liquid, the volume increases. And that happens for almost most of the substances in general. But then what happens in water, and what is the hint here in this question, is that water expands on freezing. So that means the volume decreases when it changes from solid to liquid. So that is manifested as this negative slope that we see in P versus T graph. Okay. So this is the phase diagram of water. You are correct. But here what you have to remember is that this nature of water, that water expands on freezing, results in, or you can say that one can explain this in terms of this phase diagram, and that is manifested as the negative slope in the P versus T graph. And this can be understood from just looking at the Clausius-Clapeyron equation, which one can derive from the Maxwell's first relation. So in a way, Maxwell's relations, okay, is there, okay. So in a way, this Maxwell's relations can be used to find or explain or describe this kind of physical processes. Okay, clear to everyone? Okay,
Yeah.
yeah. Okay, okay. Now, the next thing that we want to do, the next question is that we want to show that we know Cp by Cv is equal to gamma, but then we also want to show that this is equal to the ratio of adiabatic to isothermal elasticity. Okay, so the expression for uh, adiabatic elasticity Es is given by the one here, and the isothermal elasticity is given by the one here. Okay, so it's at constant entropy. This is at constant temperature. But now, can you tell me how to proceed with solving this question? What is the first thing that we will be doing?
To using Maxwell relation.
Yes. So we will use Maxwell's relations, and let's see how. So what we will first do is that we will break it. We'll break this partial differentials in terms of, so it's del P del V at constant entropy. So we will write it as del P del T at constant entropy into del T del V at constant entropy. And we all know that this is correct, right? Okay. So that's how we break up this, the numerator and the denominator. And then we use the Maxwell's relations. So all of them, we use the respective Maxwell's relations. And then how do we get from here to here? Is this clear to you? Like when you look at the solution, can you understand how we are getting from this step to this step? Can anyone maybe unmute and tell me?
So yeah, ma'am. Just to, uh, to use the relation.
Which relation? What
It is using cyclic differentiation. Sorry, differentiation. Cyclic differentiation.
is it? But
Yeah.
then if it is cyclic differential, see here it's at constant pressure, then it's at constant volume. So if we do a cyclic differential, that should come out to be at constant entropy. But we don't
Just
have that expression here.
okay, okay, ma'am. Understand.
Others can also try. Others have any idea how we go from this step to this step? Okay, so let me
Uh,
tell you.
uh,
Okay,
Using
okay, tell me.
Maxwell relation. Maxwell relation
Okay, so
also.
So from here to here, we are using Maxwell's relation. That is clear to me because we know that. So you're replacing this by this, and so these are, you can find the correspondence. That's fine. But then, how do you get from here to here using Maxwell's relation? It's quite simpler than that.
Okay. I have also. It is using just one equation I have seen before some time.
Hmm.
It is del x upon del y into del y upon del z and del z upon del x equal
Hmm.
to minus one.
Hmm. Hmm. The
And
cyclic relation. Okay.
yeah,
But in that cyclic relation, if you look back, there are three terms, right? And then in each of the cases, the constants, like here, it's with respect to pressure being constant. Here, it's with respect to volume being constant. Now, the next term, whatever term it should have been, that should have entropy being constant, right? But we don't have any such term here. So it's not coming from cyclic relations, but it's quite simple. So if you just look at this expression, there's something common between these four terms, the two on the top and the two in the denominator.
it is also coming from Jacobian relation.
Yeah, just don't think about in terms of, like the different terminologies, like maybe Maxwell or maybe Jacobian, or just look at this and think. It's pretty simple. You don't have to think about formulas here. Just looking at it will tell you. But you have to think which terms I have something in common here. Something is common in between these four terms. So you can pair them. If I tell you the answer, you'll understand that it's very, very simple. You don't need to have any, don't need to remember any relation here in order to go from this step to this step.
Yeah, this
In the numerator, in the first term, dou v by dou v, or del v by del v at constant pressure. In the second
Correct.
term, del b by del b in the numerator, common term.
Yes.
So
So what?
the
Correct.
remaining terms are del s by del p at at constant pressure divided
Hmm.
by del s by del t at constant volume.
Correct. Very good. So what we do here is we pair up this two term and then we pair up this two term. So if you just look at this two term, it is del S del V at constant pressure, and then it's in denominator. So if you multiply, it will be del V del T at constant pressure. So then the V gets cancelled, and what you get is del S del T at constant pressure. Just looking at this term and this term. And similarly, now if you work with this two term, you'll get to this expression. So in this way, you can, so in all of the situations, you don't have to like think like which everywhere you are not planning to use Maxwell's relation. You have already used the Maxwell's relations in coming from this step to this step. Now it's just normal partial differential relations which we use, and we get to this expression. Correct? Clear? I'll consider that it's clear. Okay. So now this is the next question. So you have the equation of state of a substance, which is given by this expression here. So you need to find which of the following is true. So how do you plan to proceed with this? You have to find this expression. So let me first tell you how to get to this expression. Okay, this relations are very important. These expressions of finding how specific heat can depend on pressure
uh,
or
uh,
specific.
equal to
Yeah.
ds upon dt. Can we put
Can
Cp
you
at ds upon dt at constant pressure?
CPS TDS dq by
Uh,
dt at constant pressure. So that is equal to T into ds by dt at constant pressure. Correct? And then how do you plan to proceed? So maybe I'll tell you the first part, and then you can use that concept in the later part. So here you can see that if you start with the Maxwell's relation, this is the Maxwell's relation. Okay. Now, what we do is we differentiate both sides with respect to temperature, keeping pressure constant. So what we get here is a double derivative, as you can see. And here, this is the term. Now, here you have to remember that S is again a state function. So it's an exact differential. So this is the property of exact differential, which everyone should remember, is that the order of differentiation does not matter. So here it was del T of del S del P. You can change it to del P of del S del T. And then you can replace this term here by Cp. So this relation is very important because this tells us how this specific heat changes at constant pressure changes with pressure at a during an isothermal process. So if this is the expression, can you now tell me how to proceed with the thing? Now it's pretty simple, correct? So can you tell me what should be the answer?
Differentiate with the second order. I am
Yes.
saying in this sense actually. And
Hmm?
actually, I was saying in the similar way.
Okay, very good. Okay, okay. So can you tell me what the answer should be?
Yeah.
What about others? Others can follow? Maybe can I get some response for others as well? Everybody is quiet.
Option A.
Option A. Okay. Is it option A for everyone? I guess it should not be option A. You can just try your checking your calculation.
Uh, B, ma'am.
B. Okay. So it's
Yeah.
because you differentiate it twice, right?
Ah,
That's how you
yeah.
get it. And then you multiply by T. You remember to multiply by T. Correct. That is very important. Otherwise, your answer will be wrong.
Yeah, yeah.
Okay. So
So
what you
B is
do?
right. Yeah.
Hmm? Yes.
And I got it.
S-
Answer.
Yes. Yes. So this is your volume. You differentiate it twice, multiply by T, and this is the expression that you get. So it's good to remember this kind of exercise, that if you have this Maxwell's relation, can you find how specific heat changes at different conditions? Okay, these things are very useful in solving questions and even understanding systems. Okay, so now this is the this is the expression we want to derive. So the last one was for the specific heat at constant pressure. Now this is at constant volume. So can you tell me which Maxwell's relations to use? By looking at this expression, if you are said, which Maxwell's relation will you start with? So look at this term here. So this will tell you which Maxwell's relation to start with. It is this one. Okay. And once you start with this one, how do you plan to proceed? We want to find double derivative. So in this side, we have double derivative with respect to temperature. So what we do is we differentiate this with respect to temperature. So if you differentiate with respect to temperature, this is what you get. And then again, we use this relation that it's a exact differential, and then we interchange the order, and then we can replace this term by CV, and this is what we get. So it's good to remember this, or remember how to derive these relations. it comes quite handy in solving questions. Okay, so now the next question. So here the equation of state of a thermodynamic system is given as P equal to AT cube by V, and this is your internal energy. And then we know that Ft depends only on temperature, and these are all constants, and we want to find the value of B and N. Okay, so the hint is we have to start with the first law, and then we have to write ds in terms of the different partial differentials of u, because u is what is given to us. And then we use the concept that S is an exact differential. So working on these lines, can you try solving the questions? I'll give you some time. You can try solving and then we'll discuss the solution. Everybody is so quiet. I can't understand if you are following. Can you guys just respond for me to
Yeah,
understand?
I'm
Everybody is
asking.
following, right? Others,
Yeah.
others. What about
Follow,
others? Yeah,
follow.
yeah, okay, okay. So in that case, just try to solve it out. We'll spend some time trying to solve it and then we'll discuss the solution. So you can write from the first law TdS equal to du plus PdV. Then try to expand du in terms of V and T, because this is what these are the variables here in this expression. And then use the concept that S is an exact differential. Are you guys trying or should I give you the solution?
Trying, ma'am.
Okay.
There is some integration part, ma'am. I
Hmm?
think. Uh, integration process also there in the question, ma'am.
Yes, integration, like you don't have to like literally do it like very seriously complete integration, but you have to use this concept of exact differential. Once you find the expression for ds, and then there's a comparison that involves after you find the expressions, comparing both sides and then finding the expression. So did you guys find the expression for ds and see if this matches? So the answer you'll see how this comes out, but so this is the expression. So this is what I was telling. First start with the first law and then write it. So is this matching with what you are getting?
Yeah, ma'am.
So this is matching, right? And then what is the concept that we will be using is that S is an exact differential. So that means, so this term here can be written as del S del T at constant volume. And this term can be written as del S del V at constant temperature. And then what we do is we differentiate these two terms. So we so if this term is del S del del T at constant volume, and then we differentiate it with respect to volume. And here this term is del S del V at constant temperature, and we differentiate it with respect to volume. So if with respect to temperature. So if you do that, that means the relation that we are using is del square S del T del V is equal to del square S del V del T. So the order of partial differentials do not matter. And then what we do is we compare the different terms. Is this making sense?
Yeah, ma'am.
Clear for others? So this is a very fundamental concept of exact differential, that the order of partial differentials do not matter. And that comes in use in different kind of problems. Like as you have been seeing in the last few questions, we have been using this concept. So it's a very important fundamental concept for partial differentiation. Okay. So now this is another question. So in stretching a rubber band, this is your Gibbs. This is how the Gibbs free energy depends on different factors. Okay, it's written in terms of the differentials. And now, which of the following is true? So how do you plan to proceed? Can anyone tell me how to proceed with this question?
Yeah. Yeah, ma'am. Just wait. I am doing.
Okay.
Differentiate both sides with respect to else. Okay.
Differentiate both sides.
With respect to L. Uh,
Okay. Hello. Okay. So
okay, ma'am.
different.
I'm doing.
Okay. Okay. Try it out. Try it out. Others also please try. It will be good to have response for others as well, because I can't understand if you are following it, whatever is going on. If you find any doubts, just let me know, okay?
DG equal to, ma'am. DG equal to GDP minus SDT. I'm missing. I think I got wrong on this.
DG equal to. So this is your this is, you know how to get to this, right?
Yeah.
Yeah, okay. So then where is the confusion you are saying?
Actually, I have written in wrong way. That's why I'm getting it.
See, look at one thing that in most of these cases, you have pressure as constant.
Yeah, yeah, yeah. I am scaling with the pressure as a pressure. We write F, and as a volume we write L.
As a volume, you,
Actually I am mapping with other point like pressure and volume quantity. That means extensive intensive.
yeah, yeah, that is fine. So always like pressure is an so volume is an extensive quantity, pressure is an intensive quantity. Here F will be an intensive quantity, L will be an extensive quantity. That is fine. So that's true. But then so if this is the expression for your for the gas free energy, how do you so what is the first step that you are doing? So the first thing that you have to do is you have to try to express these terms. Like see in these expressions you have S, you have F, or you have V. So you have to try to express S, F, or V in terms of
Yeah,
partial differentials of G. Can you do that?
yeah, ma'am.
Okay. So so what is S? So one simplification that can be done is that in most of these options, you can see that the pressure is constant. So you can just, y- you know, remove this term, considering dp to be 0. So what you then get it is dg equal to minus sdt plus fdl, and then try working out from there. So can you first tell me the
It
expression
is,
for
yeah. The option is one. I am getting one.
okay, and what about others? What are others getting? Yamuna, Anushka, or Kamalesh? What are you guys getting?
Some option
Hmm? Same.
yes. E is a function of P, T, and L.
Yes, correct. So you
So,
write, you are getting the same answer?
yes, ma'am.
Yeah. Okay. So, so for
But
others, huh, okay.
the minus sign will come.
Uh, I can't understand properly. There's a problem with minus sign.
Yes, ma'am. I can't understand the minus sign.
Okay, so you are not getting the minus sign. Now let us see how we can get the minus sign. And the answer is correct. This is the correct option. So let's see how do we get to that. Okay.
Actually, I just rewrite the Maxwell relation and use the fact that P and DB as instead of F and DL to put the answer. I just
Yes, yes, yes.
shortcut
That
way.
will also
That's,
work out. Yeah. Yes,
yeah.
that will
So
also work out. That's also correct. But then we can also proceed with this thing. This process is like, this is always valid. Like even Maxwell's relations will work out if you can find the correct analogy. So that's good.
I use the theory just as we write the first law of thermodynamics in the other quantities. Uh,
Hmm. Correct.
so
Like you have to write the generalized Jacobian and then consider the generalized force and the generalized displacements, and then replace the terms here, because
yeah,
here P is constant, so you can just omit this term, and then the
yeah,
generalized force and work comes from here, so you can replace those terms here and here, and correspondingly you'll get the expression. So that is correct. But so the other very that for that you have to remember the Maxwell's relations, but you can also proceed directly with what is given to you in the question. So if you consider P to be constant, you get this expression. Now we can write dg in terms of partial differentials like this. So that gives us del g del t at constant L. So pressure is already constant. So at constant pressure and L gives you minus S. And here del G del L at constant pressure and temperature gives you F. So see, from here the minus sign comes. Did you get this expressions, Kamalesh?
Yes, ma'am.
Okay. So then what you do is, now G is an exact differential. So the orders, so you do a double differentiation, and the orders doesn't matter. So automatically from there, this is the expression that you get. So the minus sign comes from the fact that you have this minus sign here. Could you find where I think there might be some mistake in your calculation? Did you find the mistake?
Yes, ma'am. I didn't
uh,
account for.
Hmm?
I didn't account for the minus S, ma'am.
Yes, yes. So always you have
you
to.
actually, ma'am, when you use the PDB, there is a just if we map with FDL constant, it is minus FDL. That's why it is so simple.
Yes, so that comes when you are mapping it. So that's fine.
Yeah,
But then you don't have to remember the Maxwell's relations for solving this question. If you are given this quantity, you can directly explain it from the normal concepts of partial differentials. So this is always true. And then you can just always compare this and you'll find the minus sign here. So
yeah. Actually, ma'am, I think I always reduce the lots of some equation. Try to one equation to map with other. That is very useful because
yeah,
why we
that's true.
remember lots of things to write the. Actually, I think in this way,
No, no,
if we
that's exactly correct. Because if you have this expression, you can just think it like an analogous form of the normal Maxwell's relations that we have considering a hydrostatic system, and then you can derive the expressions directly. But then how do you, so this form, this differentials or working with partial differentials, that lie at the very heart of even getting to the Maxwell's relation. So it's very necessary that you have the habit of working out with partial differentials, like this relations. It is this relation from where you can derive the Maxwell's relation, right? So when you derive the Maxwell's relation from the potential, this is the concept that you use. So this is a very fundamental concept. So if you remember this, even if you forget the Maxwell's relation, you can derive them. So that's why it's good to have an idea about how to proceed with this kind of questions directly.
yeah, ma'am.
Yeah, yeah.
Yeah.
Okay, okay. So now this is another question. Here, you have a gas which obeys this equation of state and has the heat capacity which is independent of temperature. Okay. Now you want to find the Maxwell's relation involving del S del V. So how do you plan to proceed? So if you are asked to find the Maxwell's relation which involves this expression, where do you plan to start with? So think of which differentials are involved in the expressions of the potentials and which potentials to choose in order to get this expression.
First, we open the bracket in like we can write PV equal to minus PN B equal to NKBT.
See, Maxwell's relations will be always true. So there we don't
Yeah.
need to consider the specific condition that is given in this question. You can just directly use the concepts of the different thermodynamic potentials. So if you want to find this Maxwell's relation, what is the thermodynamic potential that you have to start with?
So
So it's like, what if you have forgotten the Maxwell's relation and you want to find the expression for this term? So in that case, what you have to see is, see, these are the differentials that is involved, and then you have something where the temperature is constant. So if you look at this, it has S and V at constant temperature. So there should be another, uh, the other side of the Maxwell's relation should have something where we have a
it's
dependence of
del P
temperature.
upon del T upon del V. Sorry, del P upon del T.
Yes, something which has that relation. That's fine. So what should be the you can say what should be the thermodynamic potential to start with? So in that case, what you have to see is that, see, if you look at the free energy, the Helmholtz free energy, that has this two different, so it depends on temperature and volume. So here you can see in this, so the hint is that here it's del S del V. So you are differentiating with respect to V, keeping T constant. So you have to look for the thermodynamic potential, which depends on V and T. And that is the Helmholtz energy, Helmholtz free energy. So now if you start from here, what you'll be doing is so this is your expression. And then you can just, you know, first find the expression like del F del T at constant volume, and then del F del V at constant entropy. Use the concept that it's state function, and then you'll get to this expression. But it's important to choose the correct potential. And how do you choose that is what is being told in this question. So because it's differentiated with respect to V, keeping T constant. So you need a potential which depends on T and V. That's how you come to choose that you have to first start with Helmholtz free energy. Is that clear?
Yes, ma'am.
Okay. So now, how do we calculate? So we have to calculate dE, and from there we have to show that E is only a function of temperature and N only. Okay, so it does not depend on V. That is what we have to show in the second part of the question. So how do we proceed? Here we will be using this the equation of state that is given in the expression. And how do you plan to use it? So you have to try to write the expression of E in terms of partial differentials with respect to T and V. And there you have to use this information that is provided to you, such that you only have the variables as T and V. And finally, what should happen is that the term corresponding to dV should go to 0, only then we can show that E is only a function of T. Can you understand that? So maybe, so see what we do here is we start with the first law. And in the first law, we can express the internal energy in terms of entropy and the volume, considering the variables to be entropy and volume. But then we want to write it in terms of temperature and volume. So what we do this change here. So we write it in terms of temperature and volume. We change ds in terms of temperature and volume, dt and dv. Is this clear?
Yes, ma'am.
Yeah. And then what do we do? Here we have used the Maxwell's relation. Okay. And then we separate the terms for dt and dv. So this is what. So when you are told that you have to calculate dE in terms of T and V, you have to somehow initially start with ds, but then you have to remove ds by expressing it in terms of dt and dv, and then separate the dt and dv terms. And here what happens is now you make use of your equation of state that is given in your question in order to find the expression for dp dt. And what turns out is that now if you put this value here, it gets cancelled. So that means the equation only has dependence over of temperature. And obviously here you have considered n to be constant. So that means it does not depend on v because the term with dv goes to 0. Is this clear? So all these questions give you a practice of how to work or how to deal with partial differentials, and then in which cases, depending on the available question, what are the which of the Maxwell's relations to use. Because here if you do use some other Maxwell's relations, it won't work. You have to change it in terms of T and V, and then from here you have to understand that now, okay, you have P, so that means this Maxwell's relations will be helpful, and accordingly you have to substitute. So these questions in a way tell you which Maxwell relations to use at which point of time, and how to proceed with partial differentials. Okay, so now the next question was, show that gamma is equal to Cp by Cv, that we all know. But then this is the expression. How do we get to this expression? So how do we proceed with that is you have to find the expressions for Cp and Cv, and then see that, and see here N and Kb does not depend on temperature. So in a way, Cv should also not depend on temperature. Correct? And then that will tell you that the entire term is independent of T and V. So let's see how to do that. So here, this is your expression for the heat capacity at constant pressures. So this is the first law of thermodynamics that we are using, and this is what we get. Here we see that we have taken P out because P is constant. Okay. And then we are using this concept that E is only a function of temperature, which we have already proven. So that means dE dt at constant pressure should be equal to dE dt at constant volume. And dE dt at constant volume is actually Cv, which is known to us. Is this clear? Okay. And then what we do is here from the equation of state, we get del V del T at constant pressure. So here we are using the equation of state that is given in the question. We find the del V del T at constant pressure, and this is the term that we get from there. So that gives you this expression, Cp equal to Cv plus nkb. Okay. If you divide by Cv, this is the term. So here N and Kb are independent of temperature and volume, and Cv is also independent of temperature. How do you get that? You get this expression, that's fine. But in order to say that it's independent of temperature, you have to say that Cv is also independent of uh, temperature. So how do you get that? So it's said that it follows from A, but how? Any idea?
Which equation, ma'am?
So this is the expression for gamma. Did you get this?
Yeah, yeah.
You got this expression, correct? Now you have to show that it is independent of temperature and volume. How do you do that? So you know that N and Kb is independent of temperature and volume. But what about Cv? How do you show that Cv is independent of volume?
CV something.
So what should be the relation, or what should be our way of proceeding in order to prove that? So I can just give you a hint that this comes. You can get this idea from something which which I've already discussed in some previous slides.
For uh, for isothermal compressibility, CV, to use the relation of CV from isothermal compressibility. Hmm?
Isothermal compressibility. So what do you get from isothermal compressibility? What is your answer? Tell me the complete answer.
Let me see. P by CV. Just the question. I think two, three question have been discussed sometime ago.
And that is something which I just said, that the solution lies to something which I have discussed in some slides before. But what is the concept that will tell you whether CV is dependent on volume or CV is not dependent on volume? How do you comment on that? So it tells us that it directly comes from A. A is the partial differential. If you go back, this is A is the Maxwell's relation. So how can you comment on how CV depends on volume starting from this Maxwell's relation? Any idea? Others can also respond if they have some idea. Because this is a very interesting and
I,
important
CV
concept.
is independent of volume. CV now.
You have to prove that CV is independent of volume. How do you do that? That is what is being asked here. You get this expression and you have to show that it's independent of temperature and volume. So how do you show that CV is independent of volume?
To use the CV as a ds upon dt at constant. Sorry, it is depend on temperature. Yes.
Others are clueless. Is it? Nobody is responding. What about Yamuna or Kamlesh or Anushka? What do you guys think? How to proceed with this problem to show that CV is independent of volume?
Can we use
Hmm?
P by del T?
Can you just repeat once?
We can write CV as uh, dq by dt, right?
You are telling that you can write CV in terms of dq by dt at constant volume. Is that what you're saying?
Yes, ma'am.
Yeah, that is always true. That's correct. But then, okay. So tell me
We
a simple, okay,
But
okay.
dq upon dt, that
can
means it is depends on t.
there we
That's why
can get
One at a time, one at a time. Yeah.
dq by
Uh, your voice is breaking. So see, you can always write CV as dq by dt at constant volume, and you can write CP as dq by dt at constant pressure. That is always true. But now what you have to do is you have to show whether it's dependent on temperature, whether it's dependent on volume, and how do you do that? So in order to answer that question, think of this general thing that you have some function x. So you want to show that x is not dependent on y. So how do you show that? You tell that del x del y is equal to 0. Is this clear to everyone?
yeah,
Correct. So now you want to show that CV is independent of volume. That means somehow you have to show that del CV del V is equal to 0. That will explain whether it's dependent on volume or not. Clear?
yeah, man. Yeah.
So now if you start from this Maxwell's relation, how do you get del CV del V? That's the question now.
To use the TDS equation.
So which TDS equation? There can be TDS can be written in different forms. Say,
No. This TDS no. That TDS no, because I'm just using CB as a del Q upon del T, and we write DQ TDS instead of DQ. Just in this sense.
yeah, so that is how you replace the first law, correct?
Yeah.
Yes,
Yeah.
that's fine. That's fine.
So
But
here is
then,
uh,
okay.
yeah.
So if you start with first law, even there, you have to somehow find an expression for del CV del V. How do you do that? That's the question. And I can tell you that I have already discussed this in one of the slides before.
Yeah.
So what is that if I have discussed?
Actually, I am not able to write, man, this time.
Yeah, so even for others, see, you have to just if you just go on thinking about what are the Maxwell's relations and mechanically think of replacing one expression by other, that's not how it will work. You have to look at the question and then choose which Maxwell's relation, how to proceed, which substitution to do. So only then you can solve questions. So here, see, this is the Maxwell's relation, and then you have to go to an expression which tells you that del CV by del V is equal to 0. So if I go back now, I'll tell you how that is done, and you will see that I have already discussed that. So this is the thing. You start with this Maxwell's relation. You want to find del CV del V at constant temperature. And you want to prove that this is equal to 0 because that will tell you that Cv is not dependent on V. So what you do here, do you remember now? By looking at this too, can you tell me what to do? Now you should be able to. So if you are given with this expression and you have to derive this expression, how do you do that? See, now you should be able to look at it, look at the right hand side, left hand side of both the equations and tell me. Guys, are you following? Like, because see, this should be answerable by everyone by now because this is pretty simple. Just look at these two expressions and tell me if we start with this, how do we get to this?
From Maxwell equation, ma'am.
So see, Abhiram, you have to think before you are trying to answer a question. First think. This is the Maxwell's relation. From
Yeah.
Maxwell's relation, meaning this is the Maxwell's relation that is given to you. And you want to find this expression. So if you start with this, you want to go here. Just looking at these two equations will tell you what should be the next step if you start with this. And this should be answerable by, everybody should be able to answer this. So if you cannot, ask me.
Differentiate both sides with respect to t, I think.
Correct.
Then
So
del S upon del t as a del S upon del t is CV, and the right side TDS. So shifting is in the right side.
so you differentiate both sides by del t. That is correct. And then what you do is,
We write del S upon del t as CV.
yes, so you have to interchange the order of differentiation. Is this clear? See, this is how. So you differentiate both sides by t. This is the expression that you get. And then what you do is you interchange the order of differentiation. So you write del V into del S del T at constant volume. And this is your expression for CV. So this expression tells you how CV changes with volume at constant temperature. And you can get it from the double derivative of pressure with respect to temperature. Is this clear to everyone?
Yes, ma'am.
Yeah. Okay. So that means if I go back to my question, here you have the expression for pressure. So you can write pressure in terms of pressure equal to N kBT by V minus NB. And from there you can find del square P del T square. And you'll see that if you equate it to, so that should be 0. So, and in a way that would tell you that it's that would tell you that CV is not dependent on the volume. So this is what is told here is that the independence of CV from V also follows from part A. So is that clear? You'll find that that the term does not have a volume. It's not dependent on volume. Is that clear? So if you are asked whether CP or CV or any such term, how does it, whether it's independent of some other factor. The first thing that should come to your mind is the differentiation with that term should be equal to 0. Okay?
Yeah, ma'am.
Yes. Okay. So now the next question is, the next part of the question was that if you write the expression for the internal energy or otherwise, so you start with the expression for the internal energy in terms of P and V, and then you show that for an adiabatic change, it satisfies this relation. Okay. So how do you proceed with that? So this is the expression that you want to derive. Now, is this clear how you get to this expression? Why do you only have dE equal to CV dt here? Where is the other term? Why is that not here? So generally it has, there should be,
We use the gas equation, I think, in terms of.
okay.
I'm not getting an idea of it.
Yeah, so okay. Huh. So see, if you look back here, we proved that internal energy is only a function of temperature. How do you do it? We did it here. We saw that if we replace, we saw that it's not dependent on volume because this term cancels out, and it's only dependent on temperature. So now what you do here is, so this term is CV dt, correct? So dE is equal to CV dt, and this term is 0. So that is the relation that we're using here. And here in terms of T, we replace it by the from the equation of state, replace it by this expression here. This comes from the equation of state. So what we get from here is that now we can express this in terms of pressure and volume as has been asked here. Is this step clear to everyone? Okay. So now what we do is, it's an adiabatic process. That means dq is equal to 0. So we use the first law, and there dq equal to 0, meaning we can just replace the expression for dE here, and this is what we get. So then there are two terms. It's just normal differentiation, like if you take this as your variable and then divide it by this term and a slight of simplification, and then this is the expression that you get. So from here, you have to integrate, and then this is the term. So this is in a way telling you how, if you are given certain conditions, how to reach to the correct equation of state. Or if you start with the equation of state, how do you express a certain particular type of process? Like here, it's an adiabatic process that you have to show, and you get this expression. So what you do is you have to substitute in terms of your known variables and then use the conditions. It's an adiabatic process, so dq is 0. And then do some simplifications and then integrate to get this result. Is this clear? Okay.
Yes.
Okay. So now this is another very important part of thermodynamics, is the stability criteria. So I think this is already discussed in your class. So the derivations is mostly based on this fact that when the thermodynamic systems try to reach stable equilibrium, they either have to try to maximize the entropy or minimize the internal energy. And from there, this is the general expression that we get. So here J is the generalized force, X is the generalized displacement. Okay, so now if we start with this basic stability condition, we want to derive this equations. So this inequations rather. So this inequalities in a way tell us how the different state functions change as the systems try to reach stable equilibrium. So the different state functions are like the internal energy or the Helmholtz free energy or enthalpy or the Gibbs free energy. And how does they tend to change with respect to entropy or volume or pressure or temperature as the system tends to stable equilibrium. So these are very fundamental inequalities that govern how systems tend to equilibrium, rather stable equilibrium, and it's very important to understand how we get there. Okay. So now we start with this and we see that how do we derive these inequalities. Okay. So I'll first tell you the first one and then we'll see if we can understand how to proceed with the other ones. Okay. So this is your stability condition. Now what we want to show is this. So here if you see volume and number, the number of particles or n is constant. So that means we can here, if it deals with pressure and temperature, we can replace the generalized force and displacement by minus P and V. And this is what we get. Now here n is constant and then we have constant V. So if you do that, what remains is this. This is the inequality that remains. So what we then have to do is, see, here we have internal energy. So we already know, so this is something which we have discussed in the last class. So internal energy is related to entropy by this relation. Okay. And there is temperature that is involved here. So always when you are given to prove something or you have to find an expression, try to see what is the relation between these two. What relates internal energy and entropy? It's temperature. So that means we have to find an expression which involves a derivative of temperature. So what we do here is that now we consider that if we consider S, the entropy, as a function of temperature and volume and uh, what is this condition N, and then because N and volume is constant, we remove that. So what remains is delta S can be substituted as del S del T dt, del S del T delta T. Is this step clear? Like how do we get from this to this second line?
Yes, ma'am.
Yeah. So now what happens is this is always positive. That means del S del T at constant volume and number n is greater than equal to 0. So from here we get this expression. Now what we can do is we can use this relation. This comes from the first law, right? We can explain, we can write TdS equal to du plus PdV and then replace du, like we can do as del S del E is equal to 1 by T, del S del V equal to minus P by T, and all these things that we have already done in the last class. So by using this relation, we can use this relation here, and then we get to this inequality. So this is clear to everyone, correct?
Yes, ma'am.
Yeah, okay. So now you are given this. So can you tell me how to start with proving this? If this is the expression that you have to prove, what you have to do at first? So the hint is first look at what are constants. S and N are constants, right? So if you consider them constant, this term and this term goes away. What remains is only this term. So here J has to be replaced by minus P, and X has to be replaced by V. So what you then get is something like this. Now, the fact is that you want to find something, if you look at this expression, you have to find something which relates E and V. And if you remember the expression for the internal energy, it's related by P. So accordingly, you will do this substitution. Correct? Is this clear till here? Why are we doing, why are we expanding del V and not del P? So that we get to this differential, because this is what we need. This is clear.
Yeah, ma'am.
Yeah. So now what happens is we can use this relation del P del V is less than equal to 0 just by replacing in this inequality. And there, if we use this relation, we get to the final inequality that we need. Correct? Okay. So now similarly, we have to prove del square F del T square at constant volume and number n is less than equal to 0. So that means you have to first consider V and n to be 0. And then this is what remains. Now here you have to find an expression. You have to find, see, it's F. So that means it's the Helmholtz free energy. So if you remember the partial differential form of Helmholtz free energy, you'll see that you need the expression of, so the the coefficient of temperature delta T is minus S. So that means you have to find something which has this kind of partial differentials involved. So what you do is you consider T as a function of S, V, and N, write it in terms of the differentials, considering V and N to be constant, so the other terms goes away. And then it's delta T by delta S is greater than equal to 0, which tells you that now del S del T is greater than equal to 0. We replace del S, the entropy here, from the in terms of the Helmholtz free energy, and this is what we get. Clear? Okay. So similarly, for here, it's you have to take into consideration that T and N are constants. This is what you get. Now, similarly, you have to again remember this expression. So whenever you're given one thermodynamic potential, try to first write this differential form and see that how the partial derivatives come out to be. That will tell you how to, what is the partial differential that we need. So here the partial differential that we want to have is something like this. So similarly, we take the volume to be a function of P, T, and N, then consider T and N to be constant. So it's only a function of P then. So we write it as del V del P at constant T and P into delta P square. This is always positive. So we replace it and this is what we get. Now try to remember how these things depend. So this tells you that if your system is described by the Helmholtz free energy as the system approaches equilibrium, stable equilibrium, this is how it's supposed to change. Okay. And similarly, it goes for the enthalpy. These are the two relations for enthalpy. And just have a look and tell me if it is clear to you, this derivation. It goes by the similar concept. You can try to solve it out at home by yourself. This practice is a very important. Is this clear to all of you? So always look at these terms, what remains constant. Then remove those terms, only the non-zero term remains. Then look at the partial derivative of enthalpy here and consider that what is the partial differential that you are looking for. Accordingly, choose this. So accordingly, choose to expand delta S or delta T. Is this clear to everyone? This like derivations?
Yeah.
Yeah.
I have one doubt.
Yes. Yes.
In the all the section in the all the problems, dou v by sorry del v by del p, if we take a reciprocal of
Hmm.
del p by dou v, in if we take even though if we take a reciprocal, the symbol of less than or equal to will be the same. We take a reciprocal means the symbol, if it is a greater than symbol means it should be a smaller than or equal.
So that happens when you have a sign change, right? So if suppose if 2 is or suppose -2, okay, -2 is less than 0. So now you do 1 by -2. That is also always also less than 0, right?
Okay.
So that happens if you multiply a term by minus of some value. So suppose if you multiply some factor by -1 or some negative value, or you divide by some negative value, then the inequality sign changes.
Okay, ma'am. Thank you.
Yeah. Okay. So similarly, this is how it goes for the Gibbs free energy. Okay. So here the double derivatives are always or are negative, both with respect to temperature and pressure. So try to remember, or rather than remember, understand how you are getting to this you can say the dependence, because this tells you how the thermodynamic potentials change in according to the stability criteria. Okay. So that was all. So if do you have any particular doubt regarding whatever I have been discussing till now in today's class, or maybe the last class?
Ma'am,
Anything? Huh, yes.
please go the slide on where the all thermodynamic actually minimum or maximum criteria, all the listing.
Okay. This one?
Yeah. Uh, there is some I am seeing that something connection with the maximizing entropy, minimizing internal energy. So there is 8 relation, and if we remember only 4, that will also get other 4 with the condition like if we
Yeah,
have
yeah.
the
You can, yes,
equation.
yes, you can always start with something and everything will follow accordingly. Just you have to have all the relations, you have to remember the relations. But what
Yes,
I suggest is try to remember the expressions for the different thermodynamic potentials. Like there are four basic thermodynamic potentials: the internal energy, the enthalpy, the Gibbs free energy, and the Helmholtz free energy. So it's good to have an idea about the expressions of these four things, because that is very easy to remember, and from there you can easily get to any other thing. Even the Maxwell's relations can be obtained from these four thermodynamic potentials just by using the criteria that they are exact differentials. So everybody, it's clear, right, how if you start with one thermodynamic potential, how you can get to the Maxwell's relation. That's very fundamental. So that's why I would always suggest that you have you remember or have the idea about. So you don't have to remember. If you go through the entire process, you'll see that these are the four fundamental thermodynamic potentials, and uh, these are state functions which define systems under different conditions. So if you remember those four, you can get to any equations or any partial derivatives, whatever you want to get to. So what I was meaning, yeah, yeah, yes, tell me.
If you have any trick to remember those equations or any hint,
So
the
uh, uh,
potential or
see, the first thing that you have to remember is that, oh, okay, so these things come, like if you look at how you start with, see, this is the first, you start with the first law, then you just include the fact that dq equal to tds, and you get to this expression. So this is the very fundamental first law with the fact that dq equal to tds. And then when you define the system, when so under so if you say that, see, you want to describe a system in terms of your entropy and pressure only. So here the functions are entropy and volume. Now you want to define a system which is which can be described in terms of these two variables, the entropy and the pressure. So in that case, you have to use enthalpy. So if you remember this, you can very easily find this. But how you get to this is in fact the way of, so see, like these things, it can also be derived from, statistical mechanics by considering the different kinds of ensembles, which will gradually come to in the later classes, that how these are state functions and under what conditions these are the state functions that we have to choose. But so this whether you have to choose enthalpy or you have to choose the Helmholtz free energy or the Gibbs free energy as your uh, state function depends on what kind of system you are working with and what are the variables that describe your system. But these are the so if you just have to remember, for now you have to remember in the sense that if you once get to this, you'll understand. So you start with internal energy, and then when you want to describe your system by this variables, you can say that I define my system by this state function, which is enthalpy. And so that's how you get to the expression of the state functions. And once you get to that express the definition of these different state functions, only these things matter.
By
Is it
remembering attributes of the equations, we find the potential equation. Hmm?
Yeah, can you just repeat once?
By remembering the equations of variables of equations, we easily find the thermodynamic potentials.
Yes,
So
correct,
if you want
correct.
to find the entropy, what thermodynamic potential means, we have to find the equations H is equal to U plus PV.
Yeah, so you have to start with this condition, like, so uh like how do you define a system? So under certain conditions, certain functions will be considered as the state functions. Okay. So from there you get to the definition of the state functions. But once you get this definition, you can easily do this different the partial differentials, and that tells you what are the factors or what are the the variables that affect or that describes this system.
Okay, ma'am. Thank you.
Yeah. Thank-
So what will be the next topic in the session, ma'am? Like a probability theory.
yes, yes, the next is on probability. So the different ways, the different movement calculations, and the different types of probability distributions, and all those. The next class is on that.
Yeah. And please arrange some question on random walk, especially because it is very actually recent research in the random walker problem is very useful in the research program. Like,
So research, though, see, research problems, random walk research problems are quite, so it's not new in the sense that it's a very important problem to solve, especially in 3 or 2 dimensions. So that those are already there, but you want to have questions regarding, even those questions are very important in solving, like in for competitive exams or as well. Research problems, I don't know how to. So I'm not very specialized in solving research problems, or I don't think this platform is suited for solving research problems. But we can discuss the basics and discuss some questions, maybe with like the fundamental questions which help us understand random walk. Yeah, that's an interesting topic.
actually, random walk is not talking in the course video. That's why I'm
Okay,
requesting to
so
arrange some
okay,
question.
okay, fine, fine. So I'll try to include some question from random walk. Okay. So regarding today's class, any doubt from anyone?
No doubt, ma'am. Actually, we have a feedback. The class is very good. Also, for the first day session was also very good, and this is it.
Thank you. Thank you.
it
Thank you.
it is helping to recollect only just two session. We summarize all thermodynamic relation, potential, entropy. That was the syllabus is very high, but in this two session we cover all the things, useful things.
Yeah, actually, it's a huge syllabus, and we it's not possible to complete all of it. I tried to complete some, but what I would suggest is try to practice on partial differentials and how to work with partial differentials, because this cyclic relations, or this inversions, where to invert, where to do cyclic relations, or like this facts, like this thing that we just did. I'll just show you, like this concept. So you were always thinking that we have used the partial relations, Maxwell's relations, and now let me think about some cyclic relation or something. But see, it's very simple. We can just look at this two and simplify these two terms by this. So all these things you'll get well versed if you try practicing on partial differentials. And so I'll suggest that there's no other solution than practicing this thing. So try to practice as much as possible. Uh, okay then. If we don't have any more questions, so next day maybe we'll try to do some probability theory, like the probability distributions and some moment calculations maybe. And then I'll try to include some questions on random walk as well. Okay. So thank you. Hope to see you next day. Yeah. Yes. Thank you. Thank you.
Okay, bye, ma'am.
Yeah. Bye. Bye.